Hey guys, so now that y'all have learned about empirical formula, we're going to take it a step further and talk about molecular formulas. Now, what is a molecular formula? Well, it says that, remember the empirical formula was for the simplest ratio of subscripts in a chemical formula? Well, the molecular formula represents the actual number of atoms of that element in that particular molecule, okay? So that means if we had something like benzene, whose actual formula is C6H6, and we have something called acetylene, which is C2H2, they would both have the exact same empirical formula. They have the exact same percentage of carbon versus hydrogen in that formula, because the empirical formula would be C1H1. Okay, so notice that acetylene is C2H2, that's the actual formula, molecular formula, and then benzene is C6H6. So how could we take, since they would give us the exact same percentages, how could we take the empirical formula information and tell the molecular formula apart? Let's think about this. This one has 2 carbons and 2 hydrogens, versus the empirical formula having only 1 carbon, 1 hydrogen. So looking at just that one example, what sets the molecular formula apart from the empirical formula besides the number of that element? What could we be given information-wise that we've already used in calculations that could help us? Hopefully you're thinking molar mass, and if you are, that's correct. Hopefully that would make sense, because the molar mass of C2H2 having twice as many carbons and hydrogens, that would be twice the molar mass of this empirical formula. Likewise, benzene having 6 times the number of carbons and hydrogens would be 6 times that molar mass. Okay, so the missing piece to tell a molecular formula apart from an empirical formula is just molar mass. So we're really not doing anything new that you haven't done. We're just going to use that as one more step in our problems. So let's look at an example. And we're going to skip this because we're going to apply it, and I think this is going to make more sense. In the past, I've had students copy this down, and then this is irrelevant until we get to it, okay? So here's our example problem. All right, you might want to pause the video and copy this down, because this is something that is a new type of problem that you haven't seen before. But basically, the way we're going to approach this looks like our empirical formula problems, right? Well, that's what we're going to do first. We're going to solve for the empirical formula. So we need to take let's see, we have carbon, hydrogen, and oxygen. So we're just going to set this up. Go ahead and move all these guys up real quick. So we're just going to set this up as an empirical formula problem, okay? So carbon, hydrogen, oxygen, and we're going to solve for each one. And give me just a second. Okay, so we're going to go ahead and we're going to divide by the molar mass for each one. Go into 3 decimal places. This is going to be 3.387. For hydrogen, let's do this in a different color so it all doesn't run together. Let's see, hydrogen is 5.030 because it was 5.0297, so we'll round that to 5.03. And then for oxygen, we have 3.39. We're not given a 3rd decimal place. That's fine. If we could go to 3, we would go to 3. And then the next step, the 3rd step, is to divide by the smallest one. Well, they're all really close to this one that's in red, okay? So we'll do 3.387. That gives us a 1. This is going to give us just about a 1, and then this one right here is going to give us, let's see, I think it's really close to 2, maybe 1 point something. Yeah, 1.485. So we can't round this because that first decimal place is a 1. Let's try to multiply. In this case, times 2, and that will work. So we're going to multiply everything times 2. This gives us 3, 2. Okay. So our empirical formula is going to be C2H3O2. Okay? Now, if you need to, I want you to pause this video, copy this down, or better yet, you paused it after you copied and you worked it out on your own and then compared it with this answer. Okay? But now we're going to do the next step. Before I do the next step, I'm going to go ahead and erase this work. Okay? So that I can show you how I would determine the molecular formula. So, my molecular formula is going to be some multiple of the molar mass of my empirical formula. Okay? So, my molecular formula's molar mass is always going to be given in the problem. Let's see. It tells us our molar mass is right here, 118.1. That's my molecular formula. So, I'm going to take the molar mass of the molecular formula. I'm going to divide by the molar mass of my empirical formula that I just solved for. Okay, that's going to give me some whole number. Now, if it doesn't give you a whole number, you made a mistake. And you have to go back and try to figure out what you did wrong with the empirical formula. Maybe you just found the molar mass wrong. Maybe it was that simple. But the ratio of these two should give you a whole number. So this number, okay, this number is going to be what you multiply your subscripts by. So this is the number to multiply the empirical formula subscripts by. All right? Now I'm going to erase this. And we're going to do this math. So the molecular formula is always given in the problem. It's 118.1. I'm not going to put my units in because it's going to be the same units as that molecular formula. Okay, I just have to figure out what all that adds up to equal. So 118.1 divided by, well, what's the molar mass of C2H3O2? Well, we have 2 carbons, so that's 24.02 plus 3 hydrogens, 3.03, plus 2 oxygens, that's 32. So this is 59.05. 118.1 divided by that gives us perfectly 2. So that means to get my molecular formula over here, I'm just going to multiply all this by 2. When I do that, my subscript now becomes 2 times 2, so that's C4H6O4. Okay, that's my molecular formula. Does that make sense? Hope so.